We're going to run through a slightly more complicated series solution. This is problem number 19 in section 6.2 of your book. The first thing to notice is that we're looking to center this series solution at x equals 0. And you can pretty quickly realize that x equals 0 is an ordinary point for this differential equation just by dividing through by this x minus 1, taking a look at those terms. Anyway, we have an ordinary point at x equals 0, so we're going to have our standard guess of a regular old power series solution for this differential equation. We of course need to take two derivatives of this form of our solution, and we're going to plug all that information into our differential equation. So I copied down our differential equation with our guess plugged in. We can take this x right here and multiply it into the series really easily and combine the powers on x's. However, this x minus 1 is not going to multiply into this series quite as easily. What you actually have to do is distribute the series through the parentheses. That's going to give us two different terms out of this term we're looking at right here for a total of 4 terms. Okay, let's take a look at the next step. There are our 4 terms. I'm going to multiply these x's through the series. And we'd like to combine all 4 of these series into one. In this first series here, I'll do that by making a new dummy variable, k. It'll be n minus 1 in that series. In this series here, we'll make k n minus 2. And over here, we won't change anything. In this step now, I have no n's left in any of my summations. I have all k's. Every single summation has an x to the k in it, which is great. And if we look at our lower indices of summation, there is a little bit of variety. Since k equals 1 is our highest lower index of summation, we want all of our sums to start at k equals 1. We're going to do that by pulling out the k equals 0 terms from this sum here and this sum here, and I'll write those two terms down right here. So k equals 0 in this sum is going to give us a negative 1 times 2 a sub 2 x to the 0 power. And in this summation here, k equals 0 is just going to give us a plus a naught. And now that we have 4 summations that all have x to the k in them, and they all have a lower index of summation of k equals 1 after pulling out these two terms, we can combine all 4 of those summations into one. And now we can factor out an x to the k. So really this line right here is just some gigantic polynomial. The whole thing has to be 0, so every coefficient in this polynomial has to be 0. Meaning our constant term right here has to be 0. And the coefficient of every other term, which is all included right here, has to be 0 as well. Okay, and of course we call this the recurrence relation, and this recurrence relation is good for all k values starting at 1 and counting up to infinity. Now there's the recurrence relation right here written down in a slightly nicer form. Okay, let's write down the information that we have. This equation right here tells us that a2 is going to be equal to 1/2 of a naught. And then we just have to start at k equals 1 and see what the recurrence relation gives us. The k equals 1 equation gives us this right here, which eventually tells us, I believe, if I've plugged everything in right, that a3 is equal to 1/3 a2. Alright, I've written down the k equals 2 equation right here. I want to go back to the k equals 1 relationship and say that a3, of course, can be written as 1/6 a naught, because we already know that a2 is 1/2 a naught. Ultimately, in a second order DE using this technique, our goal is to get all of our a values in terms of a naught and a1. Now this original differential equation was a pretty complicated differential equation, so I didn't expect to see any kind of a pattern out of these a values. But lo and behold, it looks like a2 is 1 over 2 factorial a naught, a3 is 1 over 3 factorial a naught, a4 is 1 over 4 factorial a naught, and if we keep going, we continue to get that pattern. This is suggesting to me that we might actually be able to find a closed form solution for this differential equation, which is pretty interesting. Now let's write out the solution that we found. Our original guess was just a basic power series. And there's your basic power series right there. We found a bunch of values for our a's. A naught and a1 are always going to be given to us in the form of initial conditions. And our pattern for all of our other a values looks just like this. Now as usual, we can group all of our a naught terms together and group all of our a1 terms together. And we have a pretty interesting result. Only one term depends on a1. That's this term right here. All other terms depend on a naught, so I factored out an a naught and wrote out the remainder of our sum in this way. Now this pattern right here is suggesting to me that this is going to be some kind of an exponential function. But I left a space. The reason I left a space is because there's actually a term missing here from this pattern. There should be a plus x right here. For what's in parentheses to be e to the x, there has to be a plus x here. So what I'm going to do is I'm going to add it in right here. And of course that's illegal, so you have to subtract it out somewhere else. I'll just put that outside. And what are we left with? Well, we have our first terms, a1x minus a0x, just going to give us some linear term. And then we have this a0 times e to the x. So this isn't always going to happen with power series solutions to differential equations, but we got lucky this time, and we were able to find a pattern and write down a closed form solution for our differential equation. Now, if we go all the way back to the original problem, we had been given initial conditions. This initial condition is a0. This initial condition here is a1. I'm just going to plug those in all the way down at the bottom. And there it is. That's the solution to the original differential equation, the very complicated looking differential equation up here. If you took that solution, plugged it into the dE, it would satisfy the differential equation. It would also satisfy the initial conditions. Alright, that was a fun one. I'll see you guys in class.